Now the fourth question. Here a beam having a cross section in the shape of I section. In the previous case it is a simple rectangular section. Now we are discussing a problem with high section, and the dimensions of its flange and web is given. 20 mm wide, overall depth it is 300 mm, thickness 20 mm for both web and flange. So this is the cross section of the beam used here, not a rectangular section, it is an I section, and the span it is 7 meter. So when we are considering this question, with the previous question, in the previous question only one type of loading is given, only a simply supported beam carrying a UDL is given in the previous question. Now we are considering, if we are considering this question, we will be having two loads, that is there will be a UDL 5 kilonewton per meter and there is a point load. So when you are having two different kinds of loads, as the steps will be there will be a minor difference in the calculating the bending moment. Nothing is different because we have to calculate the moment due to this UDL and moment due to this point load. That will be the total moment. അതായത് ഇവിടെ ഒരു UDL ആക്ട് ചെയ്യുന്നുണ്ട്, ഒരു പോയിന്റ് ലോഡ് ആക്ട് ചെയ്യുന്നുണ്ട്. അപ്പോൾ ഇവിടുത്തെ ടോട്ടൽ മൊമെൻ്റ് എന്ന് പറയുന്നത് മൊമെൻ്റ് ഡ്യൂ ടു UDLും മൊമെൻ്റ് ഡ്യൂ ടു പോയിന്റ് ലോഡും ആയിരിക്കും. നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്യാൻ പറഞ്ഞിരിക്കുന്നത് ബെൻഡിങ് സ്ട്രെസ് ആണ്. സോ സിമ്പിൾ ക്വസ്റ്റ്യൻ ആണ്, ഓൺലി ഡിഫറൻസ് ഇൻ എം ആണ്. സോ നമ്മളിവിടെ യൂസ് ചെയ്യുന്ന ഏത് ഇക്വേഷൻ ആണ്? M/I ഈസ് ഈക്വൽ ടു F/Y ഈസ് ഈക്വൽ ടു E/R. ഇതിൽ ഈ ഒരു പാർട്ട് നമ്മൾ യൂസ് ചെയ്യുന്നില്ല, വി ആർ ടേക്കിംഗ് ഓൺലി M/I ഈസ് ഈക്വൽ ടു F/Y. സോ in this problem we will be having two differences, one in the calculation of moment M and the second one it is calculation of I എന്ന് പറയുന്നത് moment of inertia ആണ്. ഇത്ര നേരം നമ്മൾ ഡിസ്കസ് ചെയ്ത പ്രോബ്ലത്തിലെല്ലാം we are having rectangular section. For a rectangular section the moment of inertia it is B dq/12, but for an I section, since it is being a built up section, we want to calculate the moment of inertia using parallel axis theorem. So that is a difference in this question, and Y also we have to calculate. In the question we are having a simply supported beam, okay, carrying a UDL of 5 Newton per meter, 5 kilonewton per meter for a length of 7 meter, and also we will be having a point load of 20 kilonewton acting at the center. So this is the given question, and here you are asked to calculate the bending stress. For that we are using the equation M/I is equal to F/Y equal to E/R is there. We are considering only the first two term. M/I is equal to F/Y. So here also you are asked to calculate F. For that M into Y divided by I is the equation. So here you want to calculate M. So here the M is the moment. This moment will be due to, this M will be due to moment due to UDL plus moment due to point load. Okay, so moment due to UDL, as we all know, a simply supported beam carrying a UDL, maximum bending moment will be WL²/8, and if you are having a simply supported beam with a point load at the midspan, maximum moment will be WL/4. So this is the difference in this question when we are compared with the previous one. The previous question there will be only one kind of loading, here we will be having two different loading. So M will be given by the total moment due to UDL and point load. So W is there, UDL is also there. On substituting the values we can have 5 into length it is 7000 in mm, 8 plus WL/4. W it is 20, it is kilonewton, 10 raised to 3 into 7000 divided by 4. So we will be getting the moment value as 65625,000 Newton mm. So this is the moment developed, total moment. Now we have the value for moment. Now we want to calculate I. For calculating I, we want to draw the I section. So in this equation now we are having M. Next we want to calculate the moment of inertia value of this section. For calculating the moment of inertia value of this I section, we want to use parallel axis theorem. Parallel axis theorem, the basic equation, moment of inertia for calculating moment of inertia about any axis AB is equal to moment of inertia about the centroidal axis, that is Ig, plus area of the section into h square. So this is the equation for calculating moment of inertia with respect to any axis. IAB is equal to Ig plus AH square. For that, here we want to calculate the moment of inertia of the section about the nodal axis. So here actually the centroidal axis will be the nodal axis. So nodal axis will be your centroidal x-axis. So this will be the CG for the entire I section, because since the section is being symmetrical to both the axes, CG will be occurring at the x-axis and our centroidal x-axis will be this axis and this will be our nodal axis. Now we want to calculate the moment of inertia with respect to the nodal axis. For calculating the moment of inertia with respect to the nodal axis, we want to divide the given I section into three areas, A1, A2 and A3. Now moment of inertia about the nodal axis, INA. For that, first we have to consider this area A1, then we have to mark the centroid, we have to mark the centroid axis. So we want to calculate the moment of inertia with respect to the nodal axis. We want to calculate INA, that is IEB. For that, first we have to calculate about centroid axis, IG, that is 200 into, this is 20 B d cube by 12 plus area of the section, that is 200 into 20 into h. H will be the perpendicular distance between these two axes, that is our neutral axis and the individual centroidal axis. This will be our h. So it will be this value from here to here. This will be 150. This will be 10. So this h will be equal to 150 minus 10, that is 140 square. Next, you have to consider the next area. Next area means you have to consider this portion only. You want to calculate the moment of inertia with respect to the nodal axis, and since it is being a symmetrical section, for the second area the neutral axis and the individual centroidal axis will be the same. So now you need to consider this AH square, because h value will be 0. So IAB will be equal to IG itself. So when you are considering the second area, B will be 10 and D will be this much distance. It is given by, altogether it is 300. Here we will be having 20. Here we will be having 20. So 300 minus 40 will be having 260. So here that will be 260 and B will be 20. So B D cube, 260 cube divided by 12. This is the moment of inertia for the second section plus the moment of inertia for the third section. For the third section, we have to consider this section only. This is the centroidal axis for that section. Okay, so moment of inertia will be B d cube by 12 again, that is 200 into 10 cube divided by 12 plus area, it's again 200 into 10 into h square. Here also this will be h. We know that from here to top it is 150. This value will be 10 centroid. So 140 minus 10. 150 minus 10 will be getting 140. 140 the whole square. Adding all those values, we will be getting the moment of inertia value for the section will be 1.8636 into 10 raised to 8 mm raised to 4. Okay, so this is the I value. Now the remaining value is y. Y means distance from the neutral axis to the extreme fiber. So this is your neutral axis and the distance towards the extreme fiber will be to the top or to the bottom. Since this is being a symmetrical section, distance from the neutral axis to the top and bottom will be same. So it will be equal to, and the y for the section, the y value for this problem it is 150. So now you can have M, Y and I. On substituting the values, you will be getting the bending stress values. On substituting M, here M value will be, substituting you will getting the value for F, that is your M value will be 6562500 into Y value will be 150 divided by I value is 1.8636 into 10 raised to 8. On solving, you will be getting the bending stress F is equal to 52.821 Newton per mm square. So this is the problem. So the difference in this problem will not compared with the previous one. The first difference is the calculation of bending moment. In the previous case, we will be having only one loading condition. So UDL is only there. So WL square by 8. In this question, we will be having UDL as well as a point load. So total moment will be given by the moment due to UDL plus moment due to point load. That is the difference. The other difference is the section. Usually, in the previous problem, we will be having a rectangular section. So its moment of inertia is given by the equation I is equal to BDQ by 1. Directly we will get it. But here, since it is being a built-up section, we want to calculate the moment of inertia using parallel axle IAB plus IG plus AH square. So that is the main two difference in this problem when compared with the previous one. Now we can move on to the last problem, and the last problem is from principal planes and principal stresses. Now our last question. This question is from principal stresses and principal planes. Data are given. A rectangular element is subjected to two tensile stresses, which are one tensile stress and one compressive stress, accompanied by a shear stress. So here in the question it is given a rectangular element ABCD is subjected to a shear stress. Shear stress is 1.75. It is given. So you can see shear stress values 17.5 megapascal, 17.5 megapascal, 17.5 megapascal, 17.5 megapascal. Then we are having 7.5. These are the values of shear stress. Then we are having normal stresses acting on a member 70 megapascal, 70 megapascal. Since it is acting outside, this can be considered as tensile stresses, and this stress acting along the y direction, it is into the member, so it is compressive in nature. So this is the main point that is you have to keep in your mind when you are doing the problem. Here tensile stress, compressive stress, sigma x, stress acting along x direction, stress acting along y direction. Problem നമുക്ക് എക്സാമിന് ടെൻസൈൽ ആയിട്ട് ചോദിക്കാം, കംപ്രസീവ് ആയിട്ട് ചോദിക്കാം. ഈ ഒരു ക്വസ്റ്റ്യനിൽ one is tensile and the second one is compressive. രണ്ടും ടെൻസൈൽ ആയിട്ട് തരാം, ഒരു ടെൻസൈലും ഒരു കംപ്രസീവ് ആയിട്ട് തരാം. അപ്പോൾ ഇവിടെ നമുക്ക് തന്നിരിക്കുന്നത് ഒരു ടെൻസൈലും ഒരു കംപ്രസീവാണ് ഈ മെമ്പറിലാക്കിയുള്ള സ്ട്രെസ്. ഇവിടെ നിങ്ങൾക്ക് തന്നിരിക്കുന്ന വാല്യൂസ് വേണമെങ്കിൽ നമുക്ക് നോട്ട് ചെയ്യാം. സ്ട്രെസ് ആക്ടിങ് along x direction, sigma x, that is a normal stress, that is 70 megapascal. Then along y direction, that is 35 megapascal. This is 35 megapascal. You have to give a minus sign for this is compressive in nature, and the shear stress for it is 17.5 megapascal. So these are the data given in the question. So keep it in mind that here you have given negative sign for what it is compressive in nature. So we have given negative sign. That is the difference in this problem, or this is the main point you have to keep in your mind when you do this problem. The sigma y value is negative since it is being compressive in nature. And regarding principal planes are those planes in which shear stress value will be 0. These planes will be having only normal stress. Shear stress value will be 0 in this plane. So here, if you are considering the principal planes, we will be having one plane in which the normal stress value will be maximum. That plane is called the major principal plane, and the stress corresponding to major principal plane is called the major principal stress. And there will be a plane, and in that plane also shear stress value will be 0, but it will be less. It is called the minor principal plane, and the stress corresponding to minor principal plane is called minor principal stress. So first thing in the question we have to calculate the principal stresses. Second thing, direction of the planes. Third one is maximum shear stress and the orientation of maximum orientation of plane having maximum shear stress. So these are the 4 values we want to calculate in this section. So we can discuss one by one. So the first thing, magnitude of principal stresses. Only we are having 2 equations, direct equations for calculating the principal stresses. So we can look into the equation. Now we can look into the first part of the question. First part of the question is to calculate the principal stresses. Okay. So we have 2 principal stresses. One it is major principal stress, and the second one is minor principal stress. Okay. So for major principal stress, the equation is you can take major principal stress as sigma 1. This is given by the equation sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 the whole square plus tau square. And the second one, minor principal stress, that is sigma 2, that is sigma x minus sigma y by 2 plus root of the value is minus here, sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 the whole square plus tau square. So the difference is here one will be positive value, the other one will be negative value. So the first equation will give the value for major principal stress and the second will give the value for minor principal stress. So we can have the values for sigma 1, sigma x, sigma y and sigma 2. From the figure, sigma x is 70 megapascal, sigma y is minus 35 megapascal, and the value for shear stress destroyed is 17.5 megapascal. So directly when you substitute these values, we will be getting the value for sigma 1 and sigma 2. Sigma 1 is equal to sigma x plus sigma y by 2. That is 70 plus minus 35 divided by 2 plus root of 70 minus 35 by 2 the whole square plus 17.5 the whole square. On solving this, we will be getting the value for sigma 1 as 72.93 Newton per mm square. Okay, and sigma 2, on substitute the equation, we will be having sigma x plus sigma y by 2, again 70 plus minus 35 by 2 minus root of 70 minus 35 by 2 the whole square plus tau square. What is that? 17.5 the whole square. On solving, the values we will be getting minus 37.83 Newton per mm square. So this will be a value for major principal stress and minor principal stress, sigma 1 and sigma 2. First part of the question is all. Second part, we want to calculate the orientation or the inclination of the principal plane. Principal planes are planes which are mutually perpendicular to each other. So this major principal plane and the minor principal plane will be inclined at an angle 90 degree. So we have an equation for the calculation of angle for the first principal plane. For getting the orientation of the second principal plane, just add 90 with it. That's the equation. രണ്ടാമത്തെ പ്രിൻസിപ്പൽ പ്ലെയിനിന്റെ ഓറിയന്റേഷൻ കാണുന്നതിന് വേണ്ടി ആദ്യം കിട്ടുന്ന വാല്യൂടെ 90 ആഡ് ചെയ്താൽ മതി, ബിക്കോസ് ദീസ് ടു പ്ലെയിൻസ് ആർ മ്യൂച്വലി പെർപെൻഡിക്കുലർ ടു ഈച്ച് അതർ. സോ അതാണ് നമ്മുടെ രണ്ടാമത്തെ പാർട്ട് ക്വസ്റ്റ്യൻ. ഇപ്പോൾ മേജർ പ്രിൻസിപ്പൽ പ്ലെയിനിൽ ഡെവലപ്പ് ചെയ്യുന്ന സ്ട്രെസ് ആണ് മേജർ പ്രിൻസിപ്പൽ സ്ട്രെസ്, മൈനർ പ്രിൻസിപ്പൽ പ്ലെയിനിൽ ഡെവലപ്പ് ചെയ്യുന്ന സ്ട്രെസ് ആണ് മൈനർ പ്രിൻസിപ്പൽ സ്ട്രെസ്. ഇനി ഈ പ്ലെയിനുകളുടെ ഓറിയന്റേഷൻ ആണ് നമുക്കിനി കാൽക്കുലേറ്റ് ചെയ്യുന്നത്. അതിന് നമുക്ക് ഇക്വേഷൻ ഉണ്ട്. സോ നമുക്ക് സെക്കൻഡ് പാർട്ടിലോട്ട് പോകാം. സെക്കൻഡ് പാർട്ട് ഓഫ് ക്വസ്റ്റ്യൻ. Second part of the question is direction of principal planes. Okay, so direction of the principal plane can be calculated with the equation tan 2 theta is equal to 2 tau divided by sigma x minus sigma y. So this is the equation will give the direction of principal plane. Okay. For that, tan 2 theta is equal to 2 into tau. Tau value is 17.5. Sigma x value is 70 minus 30. On solving, we will be getting 2 theta is equal to 18.43. Theta will be half of that is 9.2. So here the orientation of the direction of the first principal plane is given by the value 9.2. Okay, next principal plane. Next principal plane. For getting the orientation, just add 90 with this values. So 9.21 plus 90. Okay, we will be getting 99.21. Okay, so orientation of the first principal plane will be 9.21. Orientation of the second principal plane will be 99.21. That is, these planes are mutually perpendicular to each other. So after getting the orientation of the first principal plane, just add 90 with the first value. We will be getting the orientation of the second principal plane. So this is the second part of the question. Now the third and fourth part is we want to calculate the maximum shear stress, that is maximum shear stress developed, the plane in which the maximum shear stress developed and the value for maximum shear stress. That is the third and fourth part of the question. So we can move on to the third part. Now we can have a look at the third part. Third part is the value for maximum shear stress. So we have the equation for tau max. This is the root of sigma x minus sigma y by 2 the whole square plus tau square. Also you have another equation for tau max, that is if you are having sigma 1 sigma 2 by 2, that is if you are having the values for major principal stress and the minor principal stress, we can also calculate this tau max using the equation sigma 1 minus sigma 2 by 2. Okay, so on substituting the values, root of sigma x will be 70, sigma y will be minus 35 by 2 the whole square plus tau square. What is the value for tau? It is 17.5. Okay, and the tau max is equal to tau max. We will be getting the maximum value for shear stress. Tau max as 55.34 Newton per mm square. So this is the third part of the question. Value for maximum shear stress. You can use the equation sigma x minus sigma y by 2 whole square plus tau square, or you can use tau max is equal to sigma 1 minus sigma 2 by 2. And the last part is we are asked to calculate the orientation of the plane having maximum shear stress. So the plane having maximum shear stress will be inclined at an angle 45 degree with respect to the principal plane. Another, ഏത് പ്ലെയിനിലാണ് മാക്സിമം ഷിയർ സ്ട്രെസ് ഉണ്ടാവുന്നതെന്ന് ചോദിച്ചു കഴിഞ്ഞാൽ ആ പ്ലെയിൻ കാൽക്കുലേറ്റ് ചെയ്യുന്നതിന് വേണ്ടി നമ്മൾ ഓൾറെഡി പ്രിൻസിപ്പൽ പ്ലെയിൻ്റെ ഓറിയൻറ്റേഷൻ കാൽക്കുലേറ്റ് ചെയ്ത് വെച്ചിട്ടുണ്ട്. ആ വാല്യൂസിനൂടെ 45 ഡിഗ്രി ആഡ് ചെയ്താൽ മതി. മാക്സിമം ഓറിയൻറ്റേഷൻ ഓഫ് ദ പ്രിൻസിപ്പൽ പ്ലെയിൻസിൻ്റെ കൂടെ 45 ഡിഗ്രി ആഡ് ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് എന്ത് കിട്ടും? ഓറിയൻറ്റേഷൻ ഓഫ് മാക്സിമം ഷിയർ പ്ലെയിൻസ് കിട്ടും. അപ്പോൾ നമുക്കിനി വേണ്ടത് ലാസ്റ്റ് പാർട്ട് ഓഫ് ദ ക്വസ്റ്റ്യൻ എന്ന് പറയുന്നത് planes having, we have to calculate the orientation of the plane having maximum shear stress. having maximum shear stress. So നമുക്ക് already values ഉണ്ട് principal planes in orientation, that is 9.21 99.21. Okay, അപ്പോൾ ആദ്യത്തെ വാല്യൂ പ്ലെയിൻ കാണുന്നതിന് വേണ്ടി just add the first value എന്ന് പറയുന്നത് 9.21 plus 45 degree. രണ്ടാമത്തെ പ്ലെയിൻ്റെ ഓറിയന്റേഷൻ കാണുന്നതിന് വേണ്ടി 99.21 plus 45 degree. അപ്പോൾ ഓർക്കേണ്ട ഒരു കാര്യം, for getting the orientation of planes having maximum shear stress, just add 45 degree with the orientation of the principal plane. So you will be getting 54.21, 51.41, and the second plane is 144. So now we have the fourth part, that is orientation of the planes having maximum shear stress. So for getting the planes, just add 45 degree with orientation of the principal planes, that is maximum shear stress. The plane having maximum shear stress will be inclined at an angle 45 degree with the orientation of the principal plane. So by this problem, our session is completed.